So, let us continue with our discussion. So, in this second lecture of the module, we shall be talking about various design representations. So, the topic of this lecture is design representation. So, actually what we are talking about here is that a design, we have a design. This design can be at any level, it can be at a very high level design, it can be an intermediate level design, it can be a very low level detailed design. But what we want to say is that design at any level can be visualized or viewed from three possible angles. So, we say that the three angles are behavioral, structural and physical. Behavioral means what the design is supposed to do, structural is how it is implemented in terms of the circuitry or the netlist, and physical is the actual implementation, whether it is implemented as a chip or as a module or as a cell and so on. And because of the three angles, it was proposed that it can be represented by a so called Y diagram. So, let us see how this Y diagram looks like and how it can represent the various aspects of the design from these three different angles. Okay. This is how a Y diagram looks like, whereas you can see the three arms of the Y corresponds to the three angles of visualization: behavioral, structural, physical. So, when you talk about behavioral, we basically are talking about how a circuit is supposed to behave. We are not going into detail as to how we are implementing it or how we are designing it. Okay? So, some typical ways to represent behavior are programs, well, as in high level description languages like Verilog or VHDL, specifications in various forms. For example, Boolean equations can be specifications, truth tables, finite state machines and etc. These are ways to specify behaviors. Structural domain says some kind of netlist, interconnections of registers, adders, gates and so on, maybe higher level modules, processor, memory. And in the physical domain, we are talking about chips or boards, the basic cells, transistors and so on. So, any design can be viewed from any one of the three angles. Let us look at these two diagrams, because these two diagrams actually show how we can interpret the Y diagram. Just you look at this first diagram on the left, here as you can see we have drawn these imaginary circles, these are concentric circles which are touching one of the points along each of the three arms of the Y. For example, you can see in the behavioral level we have a node called systems. The equivalent node in the structural level says CPU, memory, and equivalent one at the geometrical level says chips or physical partitions. So, what does this represent? I am just trying to show you. Say I have a computer that I want to design. This computer can represent my behavioral view. So, I specify how the computer should behave. Now, from another angle, this computer can be visualized as comprising of a central processing unit CPU. It can consist of one or more memory modules and maybe an IO module, an IO processor. So, from another angle, the same computer can be viewed as an interconnection of very high level functional blocks like CPU, memory and IO. This can be your structural view. But the same design, when it comes down to physical view, it can be one chip representing the processor, there can be another chip representing the first memory, a chip representing the second memory, and maybe two chips representing the IO. So, you will be having some kind of interconnections between them. Something like this. So, this will be your physical. So, what I mean to say is that the same design at the same level of abstraction can be viewed from three different angles. One as the behavior, other as a netlist, and the other as some components which are actually manufactured and the system is means implemented by interconnecting them, like chips in this case, right. Similarly, you can have some other examples at other level. For example, if I give you some Boolean equations, say f equal to a into b plus c, this represents a behavior. Now, I can represent this in terms of some gates, that will be my structural behavior, and these gates can be finally implemented using either NAND or NOR or some kind of CMOS cells, that will be the physical representation. So, you can have this view from any level of abstraction. So, in this diagram, if you come back to it, so as you move towards the center, you are going into more and more detail. For example, here you talk about logic here, and in structural you talk about ALUs and registers, and here you talk about macros and floor plans. If you go down, you talk about transfer functions, gates and flip flops, cells and module plans. So, as you move down towards the center, you are refining your design and making it more and more detailed. Okay? This is one way of interpreting the Y diagram. Now, this Y diagram can also be expressed or interpreted in a slightly different way, as the diagram on the right shows. See, here the arm here shows behavior, this is structural and this is physical or geometric domain. Now, you see, instead of circle, we have drawn some kind of a helix which starts from here and it moves down towards the center. Okay. This actually represents a top down design. How? It says that to start with a behavior, let us say an algorithm. This algorithm specification you first synthesize or decompose into a structural design which consists of some interconnection of, as I said, some processors, CPUs, memories, IOs, etc. Now, this netlist you translate into physical domain where you do some kind of a chip level floor plan, like you decide that on your chip you can place your processor here, first memory here, second memory here, the IO chips here. So, you do a tentative floor plan on the silicon, how you will be placing the different very high level modules here. Okay. Now, from here again you go follow this path. This says finite state machines, not only finite state machines, it can be some kind of logic specifications also. So, each of these blocks you again go to behavioral domain and you try to specify what these blocks actually try to perform. What is the functionality of the CPU, what is the functionality of the memory, and so on. And each of these again you will be traversing this path, this synthesis, you will be translating them into processors, ALUs, registers, etc. Register, ALU, multiplexer. From here again you will go to placement of the modules, refining the placement. Again you go to the description of the modules. Again you go to description like gates or some cells, as we will talk about later. Then again how to place these cells, then again low level finally transistor up to the layout mask. So, you see if you follow this kind of helix approach from the outermost circle to the innermost one, you are actually following the exact process which typically we follow during the design when we go through so called top down design approach. From the high level thing we slowly refine our design and we go into more and more detailed design. Okay. Fine. So, let us look at the different levels of abstraction and see how what this represents. Behavioral representation, as I said, this specifies how a design should behave, how it should respond to a given set of inputs without specifying or telling how they are implemented. You just tell that I want this, if I apply an input of this, I should get an output of this. This is my behavior. Okay. Now, this behavior, depending on which level you are specifying, can be specified in various ways. Some of these are mentioned here, these are of course not complete. Boolean equations, you can have some kind of truth table, you can also have a finite state machine for sequential circuits, sequential functions. You can have some algorithmic description written in a standard high level language like C or Java or C++, or you can also express these algorithms in the hardware description languages like Verilog or VHDL. So, behavior can be specified in any one of these, but the point to note is that in behavioral specification you are not specifying exactly how to do, you are just telling what to do, okay, what I want, but exactly how to realize it we are not telling or disclosing that. Now, let us take some examples. Let us say we have an n bit adder which we are constructing by cascading n 1 bit adders. So, how we do this? Let us first see. Let us say we have a full adder. So, how does a full adder work? A full adder has 3 inputs, the 2 inputs A and B, 2 bits, and maybe a carry in C, and the outputs are sum and carry. Suppose if I want to design a 4 bit adder, the so called ripple carry adder, what I do? I use 4 such full adders. And I cascade them in a chain. Like suppose this is my least significant bit, this is my most significant bit, and these are the 4 full adders. So, what I do? I connect my least significant bits A0 and B0 here, A1 and B1 here, A2 and B2 here, A3 and B3 here, and you get as output this sum from this side, least significant sum, then S1, S2, then S3. Now, the carry outs, the carry out from this CY0 goes to the carry in of the next stage. Similarly, CY1 goes to C2, CY2 goes to C3, and finally CY3 that comes out, that will be your carry out of the final addition. So, this is how a 4 bit adder works. This is called a ripple carry adder because the carry might ripple through the various stages before it comes out, right. So, you can see this was my behavior and this is a structural level description where I used full adders as the basic building block and I have interconnected them, right. This is just example, I shall show this on the slide also. So, here the two descriptions that I have shown here, these are the functional descriptions of a full adder. So, when I have a full adder, the sum can be defined as this Boolean equation or A XOR B XOR C, and the carry is defined as AB or AC or BC. Okay. These are the expressions for sum and carry in a behavioral fashion. Now, you see this is the first look of a specification of a circuit module using a hardware description language. This is Verilog. This is how a Verilog program looks like. So, as I said, the carry function is AB or AC or BC. So, you see how I have written a module for the carry. You see the syntax is very similar to C, like a function I define. I start with a keyword module, then the name of the module, then the parameters. The full adder will have two outputs, carry out. This carry is not a full adder, only the carry part. The output will be carry and the inputs will be A, B and C. So, I declare the input variables, I also declare the output variables. Then I assign, this is AND and this is OR, A and B or B and C or C and D. Now, you may say that I have mentioned AND and OR. So, this is as good as structural, I have mentioned the gates. Why I call it a behavioral description? The reason is, if I specify it like this, so I really do not know how this will be finally implemented. It can either be implemented as 3 AND gates, implementing the 3 product terms followed by an OR it can be implemented using NAND gates alone. Both are equivalent, both these designs are equivalent. So, I really do not know when we are finally synthesizing the design into the gates, whether you arrive at this or you arrive at this. It depends on your CAD tool, how it will actually translate your specification into the final gate level netlist. So, that is why I say that this is a behavioral level description, not a structure level, because I have not mentioned the exact gate types, I have mentioned the Boolean equation A B or B C or C A. Similarly, this is another way of specifying the behavior. Here I can specify the truth table. So, here also I specify the same specification for the carry input and output, and the convention is the inputs will come first and then the output. So, there is a table and end table construct, I give the inputs then colon expected output. If some of the inputs are do not care, I can put a question mark, like if A and B are 1 and 1, then irrespective of C the carry will be 1. Okay. Similarly, if B and C are 0 and 0, then irrespective of A the carry will be 0. So, here I can make my truth table short in this way, right. So, this is also a way to represent the carry function in a behavioral fashion. Okay. Fine. Now, let us move to the structural representation. So, structural representation essentially tells you how certain modules or components are interconnected. You specify some interconnection, like these two circuits I have shown. These are examples of structural descriptions. Here I have shown there are 3 AND gates and 1 OR gate, they are interconnected together. Here I have shown 4 NAND gates interconnected together. These are examples of structural descriptions. Okay. Now, such a structural description is, as I said, nothing but a list of modules or components and how they are interconnected. This is sometimes called a netlist. Now, a netlist can be specified at various levels like gate level, transistor level, higher level and so on. So, we shall take an example. So, at the structural level, as I said, there can be various levels of abstraction, like you can have a very high level module, like if you just come back to this example I showed earlier. Here I had 4 full adders and they were interconnected. So, this is a netlist of full adders. This is at the functional or module level where my full adder is the module. Then I can have the gate level. So, at the gate level I have a set of gates and the interconnection as I have shown in the diagrams here, gate level. Similarly, I can have switch level. Switch level means the transistor level. So, each of the gate can be converted into a transistor, and circuit level means it is a further level of refinement where you have not only the transistors, but also some, you can say, parasitic elements like resistors, capacitors and so on. So, you have a circuit comprising of transistors, resistors, capacitors typically, that is called the circuit level view of the design. Now, as you can see, as we move towards the module level down to the circuit level, more and more details get revealed. Okay? As we move down, we get more and more detailed functionality and clearly more accurate representation of the design or the behavior. Fine. So, let us come back to the 4-bit adder once more. So, this is a hierarchical description of how we have created this structural description. The 4-bit adder, let us call it AD4. The 4-bit adder we had created by using 4 full adders. These are 4 full adders, and each of the full adder can be implemented by a carry module and a sum module. The second full adder can also be implemented by a carry module and a sum module and so on. So, as you can see, as I have seen earlier, that the carry module can be implemented like this, 3 AND gates and an OR gate with a function like this. Similarly, the sum can be implemented as A XOR B, A XOR C, right. So, now we shall see how we can create a structural description of this 4-bit adder using some description language like Verilog. Let us see this. This is the top level description of the 4-bit adder. So, you see, so at the at the highest level, what does your adder represent? Your adder will have sum, carry out, carry in and 2 inputs x and y. Your sum, inputs x and y are all 4-bit numbers that you represent here in terms of the array notation. 3:0 means x and y are 2 arrays whose index values can go from 0 to 3. Similarly, S is also an array, but the input carry Cin and the output Cy4, they are single bit. And intermediate connections, like if you look at this full adder again, there were 3 intermediate connections between the full adders. Okay. So, this full adders intermediate connections, we can define some wires, and we instantiate 4 copies of full adders. Add represents a full adder whose description is here. As you can see, this is a full adder where you have carry out and sum as the outputs, A, B and Cy in as the inputs. You have a sum module, you have a carry module. In this sum module, you have sum as the output, these are the inputs, carry module, COI out is the output, A, B, COI are the inputs. So, you instantiate or you include 4 such add modules, and you see just by giving the variable names appropriately, you provide with the interconnections, like your output of this B3 COI out 2 will be the input of this C out of B2. Similarly, this will be connected here, this will be connected here. So, the connections you can specify by giving the names appropriately. So, as you can see here in this diagram once more, the output of one stage is coming as the input of the other, output of one stage is coming at the input of the other. So, in the same way, here you can specify the variable names appropriately, so that this interconnection can be specified. Now, you see this is still not a complete description, because we have not yet defined sum and carry. We have defined add, we have used add 4 times to create a 4-bit adder, but now these are sum and carry. You see here we have defined carry in terms of some gates. We have not used the logic expression anymore, AB or BC or CA. We have said that there are 3 AND gates and an OR gates. The convention is AND T1 AB means A, B are the inputs, T1 is the output. Second one, A, C are the inputs, T2 is the output. Here B, C input, T3 output, and the final OR gate T1, T2, T3 are the inputs and COI out is the output. So, this is a pure structural description, because we are specifying the exact gates to be used and how they are interconnected. Similarly, the sum, we have used 2 exclusive OR gates. First one generates our output T, second one takes XOR of T and C in, generates sum. Okay. So, you can see this example actually shows you that how you can create a structural description of a full adder down to the gate level, from the behavior 4-bit adder description down to the gate level. You can have a pure gate level structural description. Okay. Fine. Now, continuing at the lowest level, you can have the physical representation. So, here at the physical specification, as I had said, that at the lowest level you specify the layout as the collection of some rectangles, as I had shown in the example earlier. The rectangles can be in various layers, it can be in the metal layer, aluminum, it can be diffusion layer, polysilicon layer, various different fabrication layers are there. Okay. So, you will have to specify the exact geometries of these layers and in which layer it belongs to. That will comprise of your physical description, from which you can create the fabrication masks and you can go to the fab to fabricate your chip using those masks. Okay. So, as I said, the physical layout is nothing but a collection of rectangles or polygons, where this is not a complete description, this is a representation, this is only a partial description I have shown, just to tell you how the Verilog description for the physical representation can look like. You see here you can specify some line called port, which is carrying a signal x0, which is on the aluminum layer, whose width is 1, whose origin is at this coordinate. So, in this way you have some primitives for the ports, the boxes, lines, everything, where you can exactly specify which layer it is running on, what is its starting coordinate and what is its size. So, in this way you can generate the final layout as well. This will be finally used for fabricating the chip. Okay. So, I think we have got a fairly good idea. Now, in this final diagram, digital IC design flow, let us have a quick look again. There are various steps of the processing: design entry, logic synthesis, partitioning, floor planning, placement, routing. These we shall be discussing in the next lectures. You see, this whole design process can be divided broadly into two parts. The first few steps are called front end CAD or logical design. The next few steps are called physical design or back end CAD. Now, as part of this course, we are more concerned about the physical design aspects. So, we shall be assuming that we already have a circuit netlist available to us, and from there we shall be carrying out the steps of floor planning, placement, routing and the other analysis steps. Okay? And of course, at every step you need to carry out simulation. These things also we shall be discussing later. So, you can carry out simulation before your layout is created, or after your layout is done, then also you can extract this circuit and you can do something called post layout simulation, which will of course be much more accurate. So, roughly this is how things work. Okay? So, I think with this we come to the end of this second lecture. So, we shall be continuing our discussion in the next few lectures as well. Thank you.